In this video we're going to derive the discrete time Laplace transforms, both the forward and inverse transform. Now this is going to be a lead-in to the Z transform, which we'll get on to on the next video. So good luck. In this video we're going to look at the discrete time Laplace transform, but before we get started on that, we'll do a little bit of revision on the Laplace transform. So if you've done the Fourier Laplace transforms course, you'll have seen a little bit of this before, but it's worthwhile going over it again just as a reminder before we begin and we make the time discrete. So we start off with our Fourier transform here. We go a function of time, and when we do the integration multiplied by our surface e to the minus I omega t, we get our f of I omega. So this is the time domain going to the frequency domain, so this is our forward transform. Now what we do whenever we do the Laplace transform is we take this function of time and we modulate it with another function e to the minus sigma t. Now if we were to make the value of sigma equal to 0, then this whole thing would just tend to e to the power of 0, which would be 1, and we'd just be back to the Fourier transform. So now you can see that if we were to take out the common factor here of t, and this line here would have e to the minus sigma plus I omega t. So we can see here then that we're making this a function not of the value I omega, but of the value sigma plus I omega. So if you like, we're extending the Fourier transform to the full complex plane in the frequency domain. So now this is a function f of sigma plus I omega. Now what we do is we replace this sigma plus I omega with the single value s, and this gives us our f of s is equal to the integral from 0 to infinity of f of t e to minus st by dt, and this is the Laplace transform you're used to seeing. So we'll quickly go through and we'll think about this in terms of a graphical representation, and once we've done the graphical representation of the Laplace transform, we'll extend that graphical representation to the discrete time Laplace transform. So let's take the Laplace transform of some random function. We'll call that function u of t. And what we'll do is we'll split this Laplace transform down into its constituent parts, and then we'll have a look at those parts in a graphical representation. So what we have here is, for this section here, u of t e to minus st, well that can be split into u of t e to the minus. Now the s is replaced by a sigma plus I omega, so we're going to have our u of t times e to the minus sigma t times e to the minus I omega t. So we're just multiplying out this little part of the Laplace transform. And we know that we can replace our value of our e to the minus I omega t with cos omega t plus I sine omega t. So again we're left with this part here, and then we can multiply this out and we're left with our u of t e to minus sigma t cos omega t, u of t e to minus sigma t minus I sine omega t. And then what we do is we integrate this side here from 0 to infinity respect to dt, and we integrate this side from 0 to infinity with respect to dt. So as you can see here, this is nothing other than what we did whenever we did the Fourier transform, but there's just an extra factor here of e to the minus sigma t in each of these. So let's go ahead and we'll look at the surfaces here, and we'll see this actually graphically. So this is the first part of our graphical representation of the Laplace transform. We have this cos omega t surface, so this is the surface here, but it's going to be modulated by this u of t e to minus sigma t. So if there wasn't any modulation, this would just be a normal cos omega t surface, which would extend off to infinity in both the time and the frequency axis. But now this entire surface has been modulated by this function u of t times e to the minus sigma t. Now u of t, let's say u of t in this instance here is just a square function, so actually a unit step. So it comes along with value 0, and when it gets to 0 it goes up to a value of 1, and it continues along with a value of 1. So we're taking this function here, u of t, and we're multiplying it by e to the minus sigma t. So e to the minus sigma t is going to be an exponential decay like this. So we've picked one value of sigma, and that one value of sigma has created this yellow function here, which multiplies the red function, and then when we multiply these two together, the whole thing modulates this entire cos omega t surface. So you get this surface here. Now what we're going to do is we're going to integrate this surface with respect to time. So we're integrating in this direction, so we're adding up all the components in this direction, and when we do that, we're going to get a value for the function omega, and it will be the purely real value of the omega function. Now we're going to go and do that same thing with the sine omega t surface. So now what we have here is our I sine omega t surface. So this is omega and this is t. Now again, this is going to be modulated by our u of t e to the minus sigma t, but we've got a negative sign in there, so I've made this modulation the negative, so in effect it's just effect of flipping it on the this axis here. So it means that our function u of t, which is unit step, is a value of 0 until it gets to 0, and then it goes to a value of -1, and it remains at a value of -1, and our e to the minus sigma t becomes this function here, which is that's our e to the minus sigma t. Now this function here multiplies that function. Whenever they multiply the two together, it then modulates this entire surface. So you get this effect here. So the sine omega t surface is changed in this manner. And then what we do is we integrate it from 0 to infinity with respect to our time axis. So whenever we integrate it there, we're just looking at the area under this curve at each of the points along the omega axis, and that's going to give us this function here, which will be a purely imaginary function of our variable omega. So finally we've got our e to the minus sigma t surface here. Now if sigma was a value of 0, we would have e to the power of 0, and e to the power of 0 is just a value of 1. So that would just be this value here, which would be a straight line. Now whenever our value for sigma was a negative value, so it's actually e to the minus sigma t, the curve here would start to decrease like this. Okay, so it'll be an exponential decay, and the further along the sigma axis, the greater the exponential decay would be. So we would have, this would allow us to have convergence of our integral. If we were to take the value for sigma was positive, so it was in this direction here, then this e to the minus sigma t would actually head off to infinity. So it would just head up like this. So we would have convergence for this side here, and we would have divergence for this side. So don't worry if you can't quite see that. We're going to have a look at it again in a little graphical format in a second. So we'll bring all these ideas together and we'll look at the actual Laplace transform in a little graphical format in the next page. So this is how we build up our Laplace surface graphically. We take our function of time here, so in this instance here our function of time is our u of t, which is a unit step. We then multiply it by our e to the minus sigma t. So this is our e to the minus sigma t surface that you've just seen. But we only pick one value of sigma at a time. So let's take a value of sigma, say this is our value of sigma 1. So this here is our sigma axis. So our sigma 1 is here, and you can see it's a decaying exponential. So this here multiplies this here, and when they've multiplied together, both of them are then going to modulate the cos omega t surface. So I've just drawn the little square to represent the cos omega t surface. So this is the time axis here, just the same as here. The time axis runs in this direction, and this is the frequency axis running in this direction. So we've got this thing multiplied by that, which modulates this surface, and it also modulates this surface here. And then we integrate both the cos omega t and the minus I sine omega t with respect to time. So when we integrate it in this direction, it means that this cos omega t will provide us the real part of the Laplace transform, but it will only do it for one particular part of the Laplace surface. So the Laplace surface here is a complex it's a complex surface, so we're going to have an I omega and we're going to have a sigma. So this plane here is a plane of all of the complex numbers, and it's only going to give us one value for our real part of the Laplace transform, and it's going to give us a value at sigma 1. So we integrate in this direction and we get this effect here. Okay, so that's the real part of one part of the Laplace surface, and we do the same for the sine omega t, and we integrate it in this direction, and it's going to give us another value here in blue for that value sigma 1. But this here is the purely imaginary part of the Laplace transform. Now, in order to actually get this part of the Laplace surface, we just take we use Pythagoras, and we square the real part plus square the imaginary and take the square root of it, and this is going to give us our magnitude. But again, that's just the magnitude of one part of the Laplace surface. But then what we do is we have to do the same thing again with another value of sigma, so then move this along to sigma 2, and we do the same thing again, and it's going to give us another part of the Laplace surface, and so on and so forth. So this value of sigma is going to range, and as it ranges, it's going to give us all the parts of the Laplace surface. So in this instance here, we picked the unit step, and we can see that the Laplace transform of the unit step here is going to be a value of 1 upon s. So whenever the value of s is equal to 0, then this whole thing is going to tend off to infinity. So we're going to get a pole at 0, and this is shown here. So we have our sigma and we have our I omega, so this is our complex frequency plane, and we have the magnitude value up this axis here. So that's a quick overview of the Laplace transform, and some of that will be revision if you've already done the Fourier and Laplace transforms course, and if you're unsure of it, you can always have a look at some of those videos in the Fourier and Laplace transforms course. So let's extend this graphical interpretation of the Laplace transform to the discrete time Laplace transform. So really what we want to do is, instead of making this time here continuous, we want this time axis here to be discrete. So I'll go ahead and change this here and this here to the discrete values, and we'll see how this affects our surfaces here and how we're able to create the discrete time Laplace transform. So here's a somewhat stylized graphical representation. So I'll talk you through this. We don't have our function, our continuous function u of t. It's now a function of the discrete variable nt, so it's u of nt. You can see the values are 0 back here, and then come up to a value of 1 at discrete points, and they're going to be separated by this distance here, t. Now this is going to multiply the e to the minus sigma t surface, but it's no longer e to the minus sigma t, it's e to the minus sigma nt. So we can see that this surface here now becomes discrete, so it's discrete in the time domain, but of course it's still continuous in this sigma axis. Now this is going to modulate the cos omega t surface, but of course it's now going to be the cos omega nt, and we're going to have our I sine omega nt. So instead of getting a continuous surface here with omega and t, it's still continuous when omega, but the t-axis is now going to be discrete. So you're going to have discrete cosines here, you're going to have discrete sines here. So we're going to have, finally, whenever we sum up all the values, now originally when we did the continuous Laplace transform, we were integrating the values with respect to time, but now those values here are no longer a continuous variable t, they're a discrete variable nt, so we'd no longer integrate in this direction, we just add up these individual components. So we're summing from n equals 0, so this is the 0, 1, 2, 3, 4, 5. So we're summing these components up, and we're multiplying the function u of nt with e to the minus sigma nt, and we're multiplying these by the two surfaces. So the two surfaces together are going to give us our e to the minus omega nt. Now I've represented this in a, say, somewhat stylized here. So what we want to do is we're going to add up in this direction. So when we add up in this direction over all of these values of sigma, we're going to create a surface here. So it will be the real part of the final Laplace surface, and we're going to create a surface here as well, which will be the imaginary part of the final Laplace surface. And in order to get the overall Laplace surface, we square this one, and we take the square root, so we just do the Pythagoras of it, and this gives us our final Laplace transform. Now the thing to note in this, and the most important thing about all of this and what we've done so far, is that by making a function discrete in one domain, so in this instance we made the function discrete in the time domain, it has the effect of making the function periodic in the other domain. So it now becomes periodic in the frequency domain. Now we've seen that whenever we've done the discrete time Fourier transform, and we've seen it whenever we did the discrete frequency Fourier transform. So whenever we make a function discrete in one domain, we make it periodic in the other domain. So this is the point here, is that this function here we get out, we get poles, but the poles go on for infinity in both directions in the I omega axis. So that is the discrete time Laplace transform is just like the Laplace transform, but it's continuous, it's periodic in the I omega axis. So we can take the graphical representation from the previous slide and build up the forward discrete time Laplace transform. So it's going to be the sum from n equals 0 to infinity of f of nt times e to the minus sigma nt times e to the minus I omega nt. We take out the common factor of nt here, and it gives us e to the minus sigma plus I omega nt, and we replace the sigma plus I omega with our complex variable s. So this is going to give us f of s equals the sum from n equals 0 to infinity of f of nt e to the minus s nt. Now this is hardly surprising, it's just very similar to the Laplace transform. The only difference is that instead of dealing with the time axis as continuous, the axis of time is now discrete, so the t is replaced with our nt here, and the t is replaced with our nt here. And the other difference is that because time is now discrete, we're no longer integrating with respect to time, we're summing up over each of the indexes of time from n equals 0 to infinity, and that's going to give us our Laplace discrete time Laplace transform f of s. Now the most important thing about this is I've put a little bar over the top to tell you that this function here is actually going to be a periodic function, and this is the most important part of what we've done in this video, is the fact that the discrete time Laplace transform is going to be periodic. Now we've seen that in previous videos. We noted that whenever we did the discrete time Fourier transform and the discrete frequency Fourier transform, whenever you made the function discrete in one domain, say for example in the time domain, you would make it periodic in the other domain. And this is what's happening here as well. We're making this function discrete in the time domain, and it makes it periodic in the frequency domain. So let's finish off by looking at the inverse discrete time Laplace transform. So again, this is rather stylized, but it'll give you an indication of what's happening. We used this little drawn here a little diagram in order to describe the forward transform. So we're going from the time domain, we're modulating the surfaces here, and then we're integrating with respect to our value nt. We're getting our imaginary real parts, and we're then working out the square of the real plus square of the imaginary, taking the root of it, and building up this Laplace surface. Now what we're going to do is we're going to go backwards. We're going to go from this Laplace surface, we're going to go back and we're going to modulate the two surfaces, the I sine omega nt and the cos omega nt, with this Laplace surface. And instead of the summation which we do in this direction, we're then going to integrate, because the omega axis is still going to be continuous. So we're going to integrate with respect to the omega axis, and we should be able to reconstruct this little digital signal. Now the point about this here is that we only need to pick one particular surface here. So we could take a cut along here at any point, and we can generate the original time domain signal by just taking one value of sigma. Now another thing to note is that whenever we integrate with respect to frequency, we only need to integrate over one of these periods, because we know that the discrete time Laplace transform surface here is going to be periodic. So we only need to integrate over one of these periods in order to reconstruct the signal. So given that, let's go and have a look at the mathematical equations that define this. So let's now look at the inverse transform. We're going to start off with this equation here, and this is the discrete time Fourier transform. So it's the Fourier transform, but it's now discrete in time, and it's the inverse transform, so it's going from the frequency domain back to the time domain. So we derived this a few videos ago, so if you can't remember that, then you can always have a look at the discrete time Fourier transform video and you'll see where that comes from. Now here's an example here. Whenever we take a function and we sample it in one domain, so we sampled this in the time domain, you can see that in the frequency domain it becomes periodic, and a little bar across the top is telling us that this is a periodic function. So we can rewrite this as f of nt is 1 upon omega s. We'll change the limits, we'll make the limits minus omega s upon 2 to plus omega s upon 2, so that's just the same as what we've got here, we've just changed it slightly. And we've also got our function, but our function is no longer a function of the variable I omega, it's a function of sigma plus I omega, which is a complex variable, and again our omega there is replaced with our sigma plus I omega. Now we want to introduce this new variable s, which is a complex frequency, which is s is equal to sigma plus I omega. So if we were to differentiate this, then we would have ds. Now when we differentiated the sigma, well the sigma is just a real number, it's just 5 or 7 or any number. So whenever you differentiate that, that goes to 0. And when you differentiate the I omega, you're going to get the d I omega. So it means that the value of d omega is equal to ds divided by I. So it means that we replace this d omega with our ds upon I. So here's the upon I bit here, so we bring the I back down here. And we can see that our limits here of our integration is going to be omega is greater than minus a half omega s, and it's less than a half plus a half omega s. But again, we're no longer using this value omega, we're actually using the complex frequency sigma plus I omega. So it means that we can rewrite this equation up here as sigma plus I omega is greater than sigma minus a half I omega s and less than sigma plus a half I omega s. It means that our limits of integration change, so these are now our limits of integration here. Now also we've got our omega s is equal to 2 pi upon t, so this is written as 1 upon omega s, so that's going to be t upon 2 pi, so we've got t upon 2 pi here, and we've also got our value of I, which we got from this little section up here when we did the differentiation. Again, we're going to replace our sigma plus I omega with the value of S. So we're going to get this equation here. Now, I've just added this in really just for completeness. I didn't want to go through the whole course and just miss out equations here and there just because maybe we didn't like the look of them or we weren't going to use them very often, but at least you've got it here and you've seen it derived and you know where it comes from. But the main point about this equation here is that we only need to pick one value of sigma on the complex frequency plane in order to reconstruct the discrete function of time, and we only need to integrate it over one of those periods of this complex plane, and it's going to give us the limits here, sigma plus I omega s upon 2 and sigma minus I omega s upon 2. So we've seen that graphically when we looked at the previous slide. So lastly, note here that we've got the limits here from n equals 0, so we're assuming that we're working with a causal system, so there's no negative value here in terms of time, but you may see this written as n equals minus infinity to infinity as well. So why bother going through this process here of deriving the discrete time Laplace transform? Because if you've done this stuff before, you've most probably never heard of it or never used it. Well, this thing here, the discrete time Laplace transform, is nothing other than our Z transform. So if you like, the Z transform is the discrete equivalent of the Laplace transform. So we'll go on in the next video and we'll extend on this and we'll see how this gives us our Z transform. So thank you for listening. I'll get you on the next video. Goodbye.